Hello, everyone. We are getting started now. So welcome to the second meeting of the Privacy Enhancements and Assessments Research Group. Since our last meeting, we have a new co-chair. And thank you, Chris, for joining us. So this is the notewell. You'll probably have seen this or will see this a lot in the upcoming week. Please note this well. Do we have a JavaScribe? Great. Thanks, Addison. Do we have a note taker? Note taker. Great. Can't see you, but Karan. Okay. Great. Did anyone have any comments on the agenda, or is there any people who would like to propose amendments to the agenda? I'm hoping not. Okay. Let's get started then. Our first talk is by Ian. Oh yeah, the official Twitter hashtag is PEARG, in case anyone wants to tweet.
Hi. My name is Ian. I've come here from Tor Project. This is my first IETF, so be nice. I'm going to talk about some work I've been doing at Tor Project and how I'd like to generalize some of the principles from that to apply them to the wider internet. And I've started working on this draft. Oh dear. Okay, the slides are not quite scrolling properly, but okay. So I've been looking at internet measurement since 2013. I worked on the Pathfinder tool for internet transparency measurement. I've been contributing to Tor project since 2015. I want to just set the scope of this early on. This isn't about the ethics of internet measurement. That's a very, very wide, broad topic. This is specifically about safety, making sure that other users of networks that you're measuring don't come to harm. This is a working definition of safety that is going to end up in the draft. And I have a GitHub issue for sort of revising this and working out how we can improve it. There's a lot of related work in this area. Some people have already pointed out other related work I didn't know about on the PRG mailing list. If you know of other related work that I haven't heard of, please do let me know. There's lots of people in different communities have come up with their own assessments of safety and ethics in their measurements, but there hasn't been much inter-community discussion on this. So I'm going to give a little bit of the background of where I'm coming from. This isn't going to be a talk about how Tor works. But hopefully I'll give you enough that you can understand what's going on. Tor primarily is producing open source code, and then there's a volunteer-run network, and this network provides security, privacy, anonymity. It's robust, it's authenticated, it provides integrity. Depending on how you use it, it gives you these properties. And we need to monitor this network and make sure that it's working, scaling okay, that it's healthy. And one of the things that we measure from this network is the number of directly connecting users. At the moment, we have somewhere between 2 million and 8 million, according to a recent paper, daily users of Tor. We can use this data to detect censorship events. If there's censorship in a country, then maybe the number of users of Tor goes up. If there's attacks against the network, maybe Tor is blocked in a country, the number of users goes down. We can evaluate when we make changes to the software, how is it affecting the performance of the software, and see how it's scaling. The philosophy that we've tried to follow is that we only handle public, non-sensitive data, and each analysis goes through a rigorous review, often by academics, before publication of data or analysis. And we're guided by the Tor Research Safety Board, which is a group of academics and Tor researchers and Tor developers. And they are basically a service for members of the Tor wider community to assess whether or not research that people want to do on Tor is safe. The three principles that we try and follow are data minimalization, source aggregation, and transparency. So data minimalization is where we try and capture only the least amount of data possible to answer the questions that we have. And the level of that detail should also be as small as possible. So it's not just about limiting the properties that we capture, but also the resolution of them. In the Tor network, we capture at relays, and the relays are operated by volunteers. We have distributed trust across those relay operators, and they are doing the aggregations before submitting any statistics. So also we make sure that the raw numbers are existing for as little time as possible, and then we throw them away as soon as we have our aggregate. And everything is open source. We publish design documents, technical reports on how we are doing things, and hopefully people are looking at these, and if they spot any problems, then we're very happy to fix them. So going back to the general case, the shortcut to making sure that you're on a network and you're performing safe measurement is to have no one else on that network. So using simulations, using test beds, this is a pretty sure way of guaranteeing that you're not going to upset anyone, unless, of course, you're running a really big simulation and upsetting all the other researchers that they can't use a simulation machine. So one case study, counting unique users of Tor. The easy way, the web analytics approach, is you're tracking all the IP addresses you've seen, and then you're working out how many unique IP addresses you saw over a day. In 2010, we came up with a method of measuring the number of users in Tor. We didn't want to count all of their IP addresses. And we saw, there's a little bit on how Tor works. The first step of a Tor client connecting to the network is it needs to have a view of the network. So it reaches out to a directory server to get a list of all the currently running Tor relays. And we can count this list of, count the number of directory requests that are made, and from that infer the number of Tor users. So we don't handle IP addresses at all in this. We have to guess how long an average session lasts, because Tor clients will refresh their view of the Tor network every few hours. But what we do get to see here is we get trends, even though we don't have exact numbers. So that's how we get this graph. And this is in an area of problems known as the count distinct problem, where you have a number of things. You want to know how many unique things there are across this data set. And a few methods have been developed of doing this in a privacy-preserving way, one of which is hyperloglog from Google. This was originally designed where you have really large data sets and you want to count the number of unique items in it in a probabilistic way. Well, for Tor, a really large data set is one IP address. We don't even want to have that. So this can be adapted for that use case to keep track of the number of IP addresses we've seen. PrivCount is another system with distributed machines with counters, and they use secret sharing to submit their results to what we're calling a tally reporter. And then the aggregate from the network can come out, but the individual counts can't be disclosed. And another system is private set union cardinality, and I'm told that currently this is computationally infeasible, but I hope that in the future this might also be an alternative. And there are a whole bunch of others as well, Report and Proclo from Google and Prio from Mozilla. So all of these schemes exist, and there's lots of work going on in this area. So I'm hoping to generalize all of this into this draft. And the next steps that I see is coming up with a really comprehensive general considerations checklist that someone could go through and make sure that they're complying with. I want to have an introduction to literature on the secret sharing and multi-party computation systems. But I think really what I want to do is describe what the properties of those systems should be and not refer to specific systems, because I'd like this draft to remain relevant for quite a while. We need to think about future computation power that might be available. So if you're saying, okay, it's fine, everything's AES-256 encrypted and we threw away the key, maybe that works for a few years, but then AES-256 is broken and then you need to rethink your strategy. I want to have some discussion on obtaining consent from users. And often in the case of internet measurement, especially if you're an IXP and you're doing PCAP captures, you're not going to get consent from every user, but you might be able to get proxy consent from maybe the major ISPs that are peering, and they have an idea of what their users want. This may or may not be something that could be considered safe, but I want to have discussion on it nonetheless. And I want to ensure that all types of possible harm are covered. So in some cases, thinking back to a study that I did with ECN transparency through the internet, we found there were some routers that you send an ECN packet through and they crash. They refuse to route future packets. Now, thankfully, those routers are gone, but that has the possibility of crashing someone's home router, which is not something you want to do at scale. So all of these issues are up on GitHub, and I'm very happy to receive any comments, discussion, pointers at existing work. And I'm happy to take any questions now as well, or any feedback or suggestions.
Do you have any questions?
I guess if there are no questions, I'll ask one. Ian. Oh, I'm sorry. John's coming up.
Jonathan Hoyland, Cloudflare. Have you ever done any metrics any tests where you compare the accuracy of your less detailed measurement to a more detailed measurement?
Yes. So going back to the 2 million number, there was a test done with the new proof count strategy, and they've discovered 8 million unique IP addresses per day. And when we revisited what we were really counting in that graph, we found we were actually counting the number of concurrent users. So while we had thought that that was the average session length, it turns out we were wrong. There are, in fact, 8 million-ish daily users by unique IP address, but then that also doesn't consider NAT and a whole load of other issues. So even counting IP addresses exactly isn't going to get us the exact number.
So, but it's reasonably accurate, or?
Yeah, reasonably accurate, and most importantly, we can see trends.
Thank you.
Hi, Stephen Farrell. So I had a quick read of the draft, and I think it's a good thing, and I hope it finds a home somewhere, whether it's in PRG or something. I think it's a good piece of work to continue. And I guess, so that was just positive feedback, basically.
Okay, thank you.
But I guess I have a question too. I mean, to what extent are you trying to reach out and get input from other people doing kind of large-scale surveys on the internet?
Definitely. All feedback is good feedback. But yeah, large-scale measurements, small-scale measurements. There's obviously different classes of measurements. So you've got your active measurement, where you're sending probes out into the internet and maybe talking to other people's servers, in which case you might incur the bandwidth costs or whatever. And then you've got the passive measurement, which is large scale.
But also, there's, for people doing active measurements, there's often a kind of a block list that they keep of who not to bother talking to because they complained once, that kind of thing. Is that covered in the draft? I didn't.
There is an issue about keeping a do not scan list.
Yeah.
And working out what the best practices for that should be. Yeah.
Yeah. So I think that'd be a good topic to cover if you can.
Okay, cool.
For remote folks, can you please have the name and affiliation clearly when you come up to the mic?
Yeah, sorry. So I have another question. You were mentioning or proof count is primarily the system that you currently use in the Tor project to do all this measurement. And I think there were discussions in the past about potentially using Prio. Have there actually been any experiments done using Prio for Tor? And can you comment on potentially the differences between Prio and proof count?
Okay, so I can't comment on what the differences are. I don't know the system Prio that well. But what I do think Prio is in the browser.
Yes.
Right. So we currently don't have any client-assisted metrics at all. Tor browser does not have any telemetry. All of our telemetry is in the relays. So if Prio is more suitable for client-assisted metrics, I'm not sure. It's possible that we might do that at some point in the future, but it's also possible that the community might not want that at all ever. So
yeah, sure.
Were there any remote questions?
Yeah. All right. Well, thank you, Ian.
Okay.
Appreciate it. Take this. Moving on to the next speaker.
Ryan, are you online?
Yes, I'm here. Can you hear me?
Yes, loud and clear.
Awesome. Thanks. So thanks for the opportunity to speak. My name is Ryan Guest. I'm a software architect at Salesforce. I work on our security and data privacy teams. My email's up here if you want to reach me after, or I'm also available on Twitter. Siobhan, can you go to the next slide? Great. It looks like there's a little lag on the presentation, but I can see in the remote video where you're at. So one of the things we'll talk about is this presentation is really two things. One, some of the techniques we use for identifying personal data in application logs. We're a SaaS provider. We have lots of enterprises using our system. We want to strike a balance between providing log analytics tools to developers, analytics folks, as well as our customers. So we actually send our logs to customers of our system so they can get an idea of what's happening in their organization. And the next slide, Yvonne. So then identifying personal data, we have really two techniques. One is sort of dictionary based, and this is a general purpose technique that can be used across many domains. We use it across acquisitions as well. So when a new company joins or merges with us, we have a sort of general purpose tool we can run against their log data or any type of data store. The main thing here is we use common names. We've started with the top 100 census names over a certain amount of time. We also look at different location identifiers. US states is a popular one, and that can give us insights onto where potential customer data may be leaking into logs. Next slide. We also have a couple formats unique to our domain. So we have user IDs. We always know start with 005, followed by 15 other alphanumeric characters. And then various different types of custom identifiers you can think of, such as AWS SDK keys are all follow a certain format. And so things unique to our domain, we can use that to grep or search through our logs to find data. And we use these to constantly monitor what's going on in our application logs. And we can derive metrics for these to see how well we're doing at anonymizing personal data. Next slide. So then from there, we go and look at, after we've found data or potential place where data may be entering our logs, how do we go and we anonymize that? And I've put together a collection of 8 of the most popular techniques we use. We use a little more than this. But really what we try to do is develop a tool set that we can share with developers. So they can have these and they can know sort of when to use one and when to use another. So it may seem self-evident, but data deletion is the first one we start. So there's certain classes of data that we don't want to see at all. So things like social security numbers, credit card numbers, we don't want any of our downstream systems to have to deal with these. So we just drop it at the start. Next slide. Our next class of data is data masking. There we take an input and we replace it with just 6 asterisks. Gives good insight into if a value is null or not. This really helps in sort of the user experience or UI type applications where you want to show a user that a value is entered, but maybe not exactly what it is. Next slide. Another technique we use is aggregation. So we generally bucket records together if we can to avoid knowing exactly what caused a specific record. This is really popular when we talk about things like error messages in our system. So a lot of times we don't care, what user generated error message, but more how many times it happened. So we'll anonymize everything we can from an error and just bucket by account. And that gives us insight into how things are doing without which user generated the error would cause the exception. Next slide. Next, similar to that is what we call generalization. So where I live, the ISPs have chronologically numbered every residence. So giving an IP address, you can pretty much drill down the exact location that someone is. One of the requests from our marketing team was they wanted to track IPs, but really they were using it to figure out sort of what the top countries using their system were. So to be able to sort of reduce the granularity, and we use a GeoIP location service and just bubble up in the logs or in analytics what's the country that the IP is accessed from. Allows them to get the same information without having to get very specific. Next slide. A similar thing with IP address that we've done is a way to use categories. So this use case is popular with our performance team, where they look at response time of our services from different places around the world. Really what they want to do is know how far away the client is from our originating data center and track performance there. So instead of using IPs, really want to know is if you can get a bucket of what the distance is, then I can use that and report on that or do analytics on that without having to know exactly where that location is. Next slide. Tokenization is also something that we do. So we keep a key value store of a set of tokens over a domain that we define. And everywhere downstream, we replace the token, or replace the value with the token. That gives us the advantage of serving things like right to be forgotten requests or data retention requests, where after a certain amount of time, we want to forget everything we know about the user. We can just delete that token without having to worry about changing it in a bunch of immutable data stores. So if we have a central key value store, we can just swap that token out everywhere the data is generated. Next slide. And I believe there's a talk later about differential privacy, so I won't go into it in much detail. But essentially what's important to us is for certain categories of numerical values, what we do is we add a small amount of noise along a fixed distribution. And we use that to add in some privacy. And so when we have large amounts of data and doing more complex machine learning models, the noise really cancels out and you can hide in the vast set of data without having your exact details exposed. Next slide. And the last technique I'm going to talk about is encryption with a set of access controls. So generally for us, this is AES 256 for encrypting data, but really brings the access controls and key management, provide some unique opportunities to do some cool things. So you can have unique keys for a customer, for a specific tenant in our system, also for a service. And you can then decide how often you want to rotate those things and how long do you sort of retain old or legacy keys after rotation. So you can do things like if you wanted to sort of wipe access to a whole service, you can just delete the key and then the downstream systems would be unable to decrypt the data. So that has some really interesting properties for, for enforcing data privacy, especially over a certain time, is most useful to us. So next slide. And thank you for letting me present some of the work we're doing. We think it's some pretty interesting stuff. And I have my contact information on the first side. If you're doing similar things or have feedback, I'd love to hear from you. And I'll be available to take some questions.
Thanks, Ryan. I know it's really late in California. Are there any questions? I had a question, Ryan. So does Salesforce plan to publish any of this work in an academic paper or like a research report?
We'd like to. We're figuring out right now, working on figuring out the best way to do that, whether it's sort of open sourcing some tools or in a more sort of academic white paper setting. We definitely want to share some of the things we're doing and get feedback on how we can improve them. So
we have a question.
Ben Kaduk, and I don't want to get too far in the weeds, but you mentioned some bits about data encryption and sort of the key management for that. And I was wondering if there was anything interesting to say about having the keys available for different services or different levels of service or different levels of access to different services, since presumably the data is only going to be encrypted with one key at a given time. But maybe I'm wrong about that.
Yes, so the data may be encrypted with one key, but with the idea that scope towards specific application logging use case, in the same log line, there may be different keys encrypting the data. So a log may have sort of a service-specific encrypted value, and then ciphertext that's encrypted with maybe a user-specific value. And then, access controls around those. We use a variety of things, but most important for that is we have a sort of a complex permission system that's built on top of our platform, where we can say, who can access certain things and who can't. And we found that to be pretty powerful.
All right, thank you.
We have one more question.
Hi, Ryan. This is Pallavi. I'm from Salesforce too. So I had a question, not about the high, encryption of the data, but of identifying customer data. Because I think to identify the data, you must be following certain regex or some known type of searches. So I think that would also be of interest because those need to be tweaked on a regular basis, just so that something doesn't slip through the cracks. And because if the identification doesn't happen, then all of these things, like something might slip through the cracks. So do you have any kind of standardization of that?
We haven't standardized it per se, and I mentioned, kind of alluded to this, it's a combination of sort of general things that you would work against any data set, but also things that are very specific to our organization, some strong assumptions we make about how the data is formatted. And we use a combination of those. Our teams right now are figuring out the right balance between how sort of strict to make things or how sort of loose, investigating some ML techniques. We've had some problems with false positives. Just to give an example, some of the web browsers user agents look like IP addresses, the version numbers. So we've hit some interesting info in false positives there. But it's really, like you said, something we're constantly refining and trying to get better at. And Salesforce, we're very metrics driven, and we try to report, how well we're doing and track that. So like you said, and make sure we're continuously monitoring this, and it's not just a point in time, but constantly going forward. How do we improve this?
Right. Thank you.
Hey, Ryan, I have one follow-up question with respect to kind of showing or asserting how effective the anonymization techniques you're using are. You had mentioned use of differential privacy as one of the techniques. And I'm wondering if you can comment further on how you choose things such as the amount of randomness budget that each client has, or like each node has, or whatever you want to use, whatever the right terminology is, and how you choose, for example, epsilon to, maximize the utility versus privacy trade-off for that particular mechanism.
Yeah, and this is something we're still very early in. But essentially what we try and do is, sort of parameterize this, and then each specific use case can provide inputs on how, like what their k-anonymity is, and how private they want things, or how less private they want things. So it's very much right now on a specific use case by use case basis. I like to get somewhere where we publish some more, general principles. But right now it's usually a cross-functional group that sort of decides those. And really we just, sort of recommend it as a general technique. So it's very much on a case-by-case basis.
Thank you. And to what extent do the general techniques basically overlap with the content of the draft that was just previously presented? Is it a lot of the same techniques that you're describing are those which are included in the data measurement draft from Ian?
Yeah, absolutely. I need to dig into that. But yeah, you're right. There's a lot of overlap, and a lot of different groups are doing very similar things. So I appreciate the opportunity to share here and sort of give, our perspective on what we've found works for us. And yeah, exactly. Feedback like that is generally appreciated.
Yeah, great. And potentially room for collaboration as well.
Yeah, absolutely.
Great. Thanks, Ryan.
Yeah, thanks a lot.
Next up, we have Nick.
Yes. All right, thanks everyone. I'm going to talk about a project called Privacy Pass, which is interesting technology in the privacy world. So as a high-level overview, it's Privacy Pass is a lightweight zero-knowledge protocol. And before getting into the details of what it is and how we can use it, I'm going to give a little bit of context as to how this came from, and in relation to Cloudflare, the company I work for, and what problem sort of inspired the solution. So Cloudflare has a service that's a reverse proxy. So if you have a website or web service and you're using Cloudflare, requests go through Cloudflare and then they come back. There's a TLS connection between the client and Cloudflare. And if something is not cached, then the request goes all the way back to the origin. And there's another little tiny red blob there, which is for bad requests, or requests that are malicious in one way or another. And this is where the problem space occurs. So in order to reduce malicious activity, and malicious activity is spam or comment spam or requests that have malicious payloads. There's several different techniques that are used online to help protect sites against these sort of things and reduce the load on websites. One of which is a user challenge. This can be in as sort of demonstrated here as a CAPTCHA. You might have seen this. And so what happens is the browser is presented with some sort of challenge to prove that it's human, and once that challenge has been passed, then a cookie is issued that allows clearance bypass for this. So one of the issues here is that the default security levels are such that for requests coming from clients for which the site has no previous information, it's very difficult to distinguish bad requests from good requests a priori. So there are situations in which IP reputation are taken into account, and if that's the only piece of information that there is, then that's the only piece of information that can be used to choose whether or not to show this CAPTCHA. And so users using VPNs or Tors or something in which the source IP is shared among a lot of users, and there's a lot of potentially malicious traffic coming from this, will be served with these CAPTCHAs more often. And solving a CAPTCHA using a cookie is not portable. This is important. This is part of the web origin policy. So every single site that you visit will be given a CAPTCHA. And so there's somewhere around 11 million domains that use Cloudflare, which make this sort of a bigger problem than it would if it was just one site and you have to solve one CAPTCHA. If you're doing any legitimate, or I guess if you're browsing the internet, you're going to run into quite a few of these sites, and it's going to be very annoying. So we want to kind of reduce that problem. And one of the ways that you could think of doing it is figuring out how to potentially solve a challenge and get back some sort of currency or some sort of proof or token or something like this that you did solve this and something that's anonymous. So wouldn't it be nice to have some sort of online equivalent to cash, so that you can do withdrawals and then make a transaction and have these two things be unlinkable. So withdrawing cash and paying for it would be unlinkable. So the analogy is actually not that great, right? So if you think of cash in a world where cameras are ubiquitous, then you have serial numbers on every piece of every bill, and so actually it is trackable from withdrawing from a bank account to paying somewhere else, as long as there's cameras everywhere. So what's sort of a better analogy here? And I would propose that a better analogy would be a self-printing money that gets assured. I'll describe how this works. So you would get a bill, put it in an envelope, put a serial number on it, and then take a piece of carbon paper. This is a very rough physical metaphor here, but put a piece of carbon paper in it, seal the envelope, send it to an official authority who would then sign the outside and say, yeah, this is an official bill. And then when you'd open it up, you would have the official bill, and the authority that has signed it would have no knowledge of the serial number. And so this would be an untrackable cash bill, if you will. And so this is the metaphor that kind of was used by David Chaum back in the 80s when he invented the idea of e-cash. And from a high level, this is based on a cryptographic property called blind signatures, or blind signing. So there's two flows here. The first is issuance of cash, and then the second is redemption, or spending it. So the way it goes from a high level is you take a token, you blind it in some way, you send it over to the authority, who then creates a digital signature using that token and sends it back, and then so you have a blind signature. And then you can take the blind signature and unblind it. And from the perspective of RSA, the way it works is the blind token and the blind signature are signed, and if you unblind them together, then the token and the signature are also correlated. So you can take the token and the signature, send them to any third party who can then validate against the public key of the issuer, and then return goods. So I may go into a little bit too much math in this, but I'll try to make it easy. But in terms of RSA, there's kind of two values. You have an E, which is a public key, and a D is a private key, and this is how a Chaumian eCash works: is you take your token K and you multiply it by a random number exponentiated by the public key, send it to the server exponentiates by its secret key, sends it back, and you can just divide out this random number and you'll get a pair K and K to the D, which is essentially a token, and a token exponentiated by the server's private key. And if you want to redeem that, you send it to any third party. They exponentiate by the public key, check to see if it matches, and if it does, then great. This is something that was definitely signed by a third party. There are some more details here, but this is the general approach: is blinding and unblinding and redemption. And so after some conversations at Real World Crypto in 2016, some folks decided to kind of write down how this could be applied, this method could be applied to solving CAPTCHAs, where you would imagine if you solve a CAPTCHA, that would be issuing a token, and then you could use that token to solve another CAPTCHA without actually having to actually put in the information. And this draft led to this idea, which is the foundation of Privacy Pass, where, yes, you have a token, you blind the token, you solve the CAPTCHA, send it to the server gives you a blind signature, and then later, if you see another CAPTCHA, you can take the token and the signature, send it to the server, and get a bypass from that, bypass that CAPTCHA without solving it. essentially. So is this it? This is privacy pass. Well, not exactly. This was our original paper that we submitted to PETS and got rejected because it wasn't that satisfying to use this slow 1980s cryptography. And there's been recent advancements in this field that are similar to things like eCache that we could have used, and we decided eventually to look into and to use. And the two fundamental ideas here are that of an OPRF, which is an oblivious pseudorandom function. This is very analogous to blinding. It's a client and a server compute a value such that the server doesn't know what the result is, but the server's required to be a part of it. And then another concept called VRF, which is a random function that is computed using a private key, and you can prove that the private key was used to compute it. And so taking these two concepts, we came up with something we're calling a VOPRF, which is a verifiable OPRF. It takes concepts from both. And I'll kind of walk through what that is. As in terms of inspirations and work, there's a lot of previous work on here. Friedman first came up with an OPRF. Urecki and all came up, had used this to do something called, do set intersection. And in 2014, the real idea of a VOPRF came about. It didn't have all the features that our final privacy pass did, but it was used for privacy, password protected secret sharing, and a type of PAKE algorithm. Later, there was a paper called Sphinx, which is about using OPRFs to do secret hiding. Sharon Goldberg presented at the CFRG a proposal about verifiable random functions based on elliptic curves. It did not include anything to do with blinding in there, or batched DLAQ proofs, which are things we use. But yeah, there's a couple other papers, including a paper by Burns, and then Ryan Henry's thesis. And taking all these ideas and kind of putting them all together, we came up with privacy pass. So what's my time like? So I've got quite a few things. We're good. Okay, great. So hopefully this will be clear, but I'll walk you through exactly how privacy pass works. There's a few fundamental things to keep in mind. One is the setting in which we're doing the computation, and the setting is a prime order group. You can imagine this as the group of points on an elliptic curve for, say, elliptic curve Diffie-Hellman, and it has to be a prime order group, which is just a small wrinkle. But in any case, group elements, I'll denote them with capital letters such as P or Q. And then the fundamental operation you're doing on these is scalar multiplication. So if you are taking a point P and multiplying it by itself n times, or adding it to itself n times, that's scalar multiplication. Oh, I heard something. Okay. And so scalars are lowercase letters. Oh, that's just next door. The last two pieces are hash to group element. This is a function that takes a scalar, a token, and outputs a group element that is random in a statistically average sort of random way, uniformly average random. And then the last piece, this is the only kind of tricky concept, which is that of a discrete log equivalence proof. This is the only place in which zero knowledge comes into play here. But the idea is that two pairs of points can be analogously related to each other. So P and R can be related to each other like Q and S using the same multiplier. So if you have P and S times P and Q and S times Q, you can prove that this S, there is an S such that, P is equal times S is S times P, and Q times S is S times Q. And you can do so without revealing what S is. So this is really used for in VRFs, and it's used in other places for proving that a specific private key was used, and these scalars are usually private keys. So this is going to be denoted DLAQ, P to R is the same as Q to S. All right, so with these fundamental pieces, I'll walk you through a naive construction of how this would work and iterate through until we've kind of ironed out all the problems. Okay, so scenario one. Client takes a point on elliptic curve T and sends it to the server, and the server has a private key, a secret number, S, and multiplies T by S and sends it back. And then later, the client will take this T and this S of T, send it to the server. Then the server can check to see that this had previously been issued by taking the T, multiplying by S, and see if it equals to the second point. And so this step is called a redeem. And this is the very naive scenario that everything here is built on, is multiplying by a secret value on the server side. Since the server knows S, you can compute S of T. So the problem here in this situation is that during the issuance and the redemption, the same S of T is sent. So these two are linkable together. So this is where we introduce the idea of blinding. So in this case, the client has a same point T as well as a blinding value B, which is a randomly generated value that it keeps on its own side. And so you take the blinded point, send it to the server multiplies by its secret point, sends it back. And then you can, because you know B as the client, you can multiply by the inverse of B and get back T and S of T, and then redeem that way. And then just like before, the server can take T, multiply by S, check if it's the same, and say, okay, great, this was issued before. And because the blinded value was never, or the value sent in the issuance is blinded, then the server actually does not have linkability. So the problem here is, this is great, but this is slightly malleable. If you have T and S of T, if you multiply them both by any scalar, say 2 or 3 or 4 or 5, then you're going to get an infinite number of valid pairs that you can redeem. So one issuance gives you an infinite amount of redemptions. So that's bad. All right, so how is this solved? Well, I remembered I mentioned hash to group element. This, if you think of cryptographic hash, it's one way. You can't reverse it. So instead of picking a point T where you start, you actually pick just a number T and take that T and hash it into a point T. And then in this case, when you redeem, so exact same issuance, you take T and you blind it, send it to the server, get it back. And then when you redeem, you actually send the token value T, not the point T. And because the server can do hash into the value T and then multiply by S, it can still validate this. And because you can't find a T that hashes into something that's a multiple of the other T, because this is a one-way function, you really can't get another pair. You're guaranteed to have a unique pair. And there's a slight problem with this situation. It's really not that big of a problem, but essentially, if you're sending this token, it's not actually bound to any specific message. So if you happen to be sending it over an insecure channel, then someone could take this and associate it with a different message. So there's a trick you can do here, and which is rather than sending S times T, rather than sending sort of the signed point, what you can do is sign a message and an HMAC of that message with S of T. And so how does the server compute this? Well, the server takes T, hashes it to the point capital T, multiplies by S, and then it has the key for the HMAC. So rather than explicitly checking that the ST that was sent is actually the same as the STs that computed, you just check that the HMAC is computed correctly, which is great. And so this goes through pretty nicely. But this is really as far as you can get with just an OPRF itself. This is essentially an OPRF construction. The problem here is tagging, is the idea that this S could be chosen uniquely for each individual, and or if there's an S that's chosen for everybody and then an S that's chosen for the one target. When you send in your redemption, then they can track you essentially. And so, what is the proof? What is the way to fix this? And this is where the DLEQ proof comes into play. Essentially, at this point, the server publishes a generator point and a generator point multiplied by its secret key, which is essentially like a Diffie-Hellman public key, and it publishes it somewhere universal, somewhere like the Tor consensus, or somewhere like a certificate transparency log, or somewhere where every client knows that this is going to be the unique value. It could be embedded into the software, which is sort of what we did. So the idea is here, when you send back the server's SBT, you also prove that SBT relative to the blinded token is analogous to G to S to the G, so that it was the same scalar that was used to multiply. This is how VRFs work. They say, okay, this is a proof that we're using the exact same S for U that is in the public domain, and this is great. So this is mostly the end of how Privacy Pass works, except that this only gives you one redemption per issuance. So the text is a little small here, but essentially we're doing this. We can do it multiple times, say 3 times. You can solve one CAPTCHA, send in 3 different tokens. The problem in this case is that these DLEQ proofs are a little bit big, a little bit expensive. So we came up with a small optimization that you can actually compress these 3 DLEQ proofs into one. And so you can issue 3 tokens and give 1 DLEQ proof for all of them simultaneously. And this is it. This is essentially how Privacy Pass works. Is when you solve a CAPTCHA, you come up with 3 unique values T, or in this case, it could be up to 30, depending on how you're configured. So let's say 30. You hash them all to points on the curve. You blind them all, send them to the server. The server multiplies them all by its secret key, gives a DLEQ proof that the same secret key was used for all of them, sends it back, and then you can individually redeem them each with this HMAC system. Okay, so this is it for the protocol. And also, I guess a year and a half ago, we released Privacy Pass as a Firefox and Chrome extension. So this is something that is really implemented and deployed with, it says 50,000 daily active users, but the Chrome extension has about 125,000 users. It wouldn't tell me how many were daily active, and the Firefox one says there's something about 25,000 daily active. So I estimated this. There's trillions of requests per week to the Cloudflare network, and in terms of redemptions, there's about 500,000 per week using Privacy Pass, and this ended up getting accepted at PETS last year. And so this isn't public domain, this information right now, as well as all the sources open at privacypass.github.io. So looking forward, we're currently integrating Privacy Pass with different CAPTCHA providers. There's a slight issue here relative to Chaumy and eCash, where anyone could validate these tokens. So VOPRFs are not publicly verifiable. You have to actually have the private key to check that the token is correct. So it's more like a voucher than cash, but it's one small downside relative to the RSA version. But the speed ups you get by using elliptic curves and by having all of the space savings really makes up for it. There's an OPRF submission to CFRG that's currently on revision 3. And we're also looking into different applications of the idea. For example, there's a draft submission for TLS to use these tokens to do anonymous resumption. There was a recent paper about how TLS session resumption is a tracking vector. This is meant to solve that. You can think of this, use this to do anonymous referral codes. That's another interesting idea we're exploring. And anything that's really a single bit of zero knowledge proof can be used for this. So if you wanted to have a Privacy Pass token that validates, that is run by, say, a government and that proves that you're over 18 or XYZ EU citizen, you can use this. It's very lightweight. There's no advanced math for that. And so with that, I will open it up to questions. And this is what the discrete log equality looks like. if anybody's interested.
Wes Hardiker, ISI. Fascinating work. I really like the intent behind it and the desire to, I guess the goals behind it as well is the way to say it. A couple of quick questions. So one, you said that there is, of course, some sort of expense, related to it. Do you have any percentage, CPU increase to actually do the level of math associated with it?
Yeah. So in order to do this from the client side and from the server side, it's really one elliptic curve scalar multiplication. So it's cheaper than a TLS handshake. Okay. So this was one of the goals. With RSA, it was slightly more expensive, and it's I guess one elliptic curve operation per token.
Okay. That's not that bad.
Yeah.
So the next question, and there will be a follow-on, is from what it sounds like, there's a limited number of tokens that you hand to clients. So maybe you hand back 30 or something like that, and after 30, they come back and they have to solve a CAPTCHA again. Is that correct?
That's right. Yeah, there's not an infinite number of tokens. So deciding on the parameters is use case dependent, and we found that 30 or so was enough that it reduced the friction for users quite a lot. And you can technically modify the code to do up to 100 on the server side, but it really depends on the use case.
And the follow-on to that is, I'm assuming that there is no reason why the client couldn't share their cookies with somebody else, that they're transferable technically if they share their secret keys with another one.
Yes, in fact, on the client side, once you've unblinded your token, then you don't have any secret state at all. You can share your, actually even with the blinded token, you can share it with anybody. So one thing to keep in mind that I didn't mention on the server side is that there does have to be some level of double spend protection because these could be potentially computed multiple times. But yeah, if all in all, there are some other larger ecosystem things that are brought up by issues like this, such as farming. You could imagine someone could do a lot of farming and solve a lot of CAPTCHAs and then kind of use it to bypass things on a wider scale. But generally, yeah, we think that having key rotation is a way to help reduce that. And metrics show that it hasn't been abused in that way.
Right. Well, that was where I was heading next. Was if a malware is distributed that took over 1 million browsers, then they could collect an awful lot of tokens to make endless use of if they needed to at some point in the future. So.
Yeah, that's right. And so it would be you're essentially multiplying or reducing the cost, but you're not eliminating it. So in order to get 30 tokens, you still have to solve one CAPTCHA. So you're multiplying the value of solving one CAPTCHA by a factor of X, where X is number of tokens.
And there's still nobody behind me. So you talked about double spending on the server side. So you actually have implemented something on that. It's not in your slides from what I saw. So you have something that's checking double spending, and is that double spending checking infinite in lifetime, or?
Yeah, so it's our implementation of double spend detection is changing. We're rewriting this to leverage a new platform that's a JavaScript-based platform called Workers that has more robust double spend protection. But essentially, you have to keep the double spend strike register as long as the lifetime of the server's private key, and so key rotation is the way to actually reduce that. And so you do get into a little bit of a chicken and the egg problem. If right now in the very first version of Privacy Pass we hard code the server's key, so we haven't been able to rotate, and so we're coming out with a new version in the next few months or so that allows that to be updated on a dynamic basis.
Well, anyway, very cool. Good work. Keep going.
Cool, thank you.
Yeah, Nick, I have a quick question. So the DLE key proof is a very elegant way to solve the key tagging problem. Were there any other earlier designs that you considered in order to address that? Like you can imagine, for example, the server signing what is the blinded token, providing the public key back, and then clients like gossiping it to see that they're all having the same view of the key.
Yeah, it all boils down to the same problem, which is key rotation and key distribution and trust of key rotation. So we did consider publishing that in places that the client can be assured of a shared global view. So something like the certificate transparency log is one way to do it, and distributing it from a central source that is signed by a long-term key is sort of the design that we're considering for the rotation going forward.
Cool. And quick follow-up question. I know there was a draft that was originally written, not submitted anywhere on GitHub, that eventually became the PETS paper that was accepted. Is there plans for a actual specification for Privacy Pass for later consumption and potentially standardization, or not?
Yes, potentially. I think that in terms of HTTP and using this as an HTTP mechanism, there's nothing that would prevent this from being standardized. We're first exploring federation with respect to, we have our own captcha provider, but we're now currently experimenting with a company that called HCaptcha that does their own captcha, as well as a company called ArcRose Labs who has something called FunCaptcha. And as I mentioned at the end, this is potentially generalizable to a lot of things. So we want to see how it plays out operationally before deciding to standardize, but I think there's definitely potential.
Cool. All right. All right. Yeah, I think.
Okay. Thank you.
That's pretty much it. Thank you, Nick.
Has anyone not signed the blue sheet?
Where are the blue sheets? Where are the blue sheets? Surely they're in this room somewhere. Oh, they're in the back. Thank you.
Yeah, next up, we have Amelia and Christopher.
So, hello, Christopher, are you connected?
Yeah, I think so. Am I? You hearing
Yes,
me fine?
you are. Yes. So my name is Amelia Andersdotter. I work for Article 19.
Yeah, and my name is Christopher Långström, and I am a master's student in applied mathematics at Uppsala University. I'm currently working on my master's thesis on privacy-preserving methods in data science and statistics.
So first, we want to thank everyone for letting us have this presentation today. This is going to be a very high-level view of differential privacy. Some of the slides will contain mathematical notation. Do not be alarmed. It looks like there's a lot of it, but it's for completion. It's in case you forgot something about exponentials or mean values. It's all in there. And it's so you can go back and review the slides without feeling that you're completely lost. So this presentation is going to be in approximately 3 parts. We'll give this very high-level overview of what does differential privacy aim to do. Then we'll go into some different mechanisms for achieving differential privacy, like input data perturbation or output data perturbation. Finally, we'll rotate back and see a few ways in which we believe that differential privacy mechanisms could be or could not be applied in IETF protocol standardization. And the very last slide contains references that you can peruse at your own liking when you have the time, that we found very useful to enhance our understanding of differential privacy. So firstly, where are we at? Well, in the IETF, we have RFC 6973 that contains privacy considerations for IETF protocols. Differential privacy is, of course, a specific way of remedying some privacy problems, such as identifiability, which is mentioned in the RFC 6973, or secondary use, which is also mentioned in RFC 6973. Differential privacy simultaneously provides a value to the degree of success that we have when trying to remedy these threats. The overall aim of differential privacy is to provide an individual with plausible deniability when you are performing a statistical test on the database, in the sense that such an individual should be able to deny being part of any database on which you have performed an aggregate query.
Right. So again, there's a bit of a delay in the slides, but I'm assuming that we have the definition up now.
Yes.
Is that true? Right. So this is our definition of differential privacy here. So this is a strictly mathematical definition, and this is called so-called epsilon delta differential privacy. So we're going to break it down piece by piece and look at what each element of it means and try to link it to the underlying meaning that of differential privacy and what we're trying to achieve. So as just mentioned, the idea in differential privacy is to make it so that any one person in a data set is not overly exposed to any sort of risks. So what we have here is we have D and we have our D prime in the notation. So these represents two data sets that differ on just a single element. So they are the same up to one row. And then we have M here, which is a mechanism which we apply to our data set. This will be something like a query, like it could be a statistic computing the mean value or the variation of something. And going forward, we're going to use the shorthand M to just mean M as applied to D, and M prime to mean M as applied to D prime. Next slide, please. So we have our P of M here, which is then our probability distribution of our mechanism M. So this is the range of all possible values that our mechanism can take, and then of course the sort of the probability that it will assume each and one of those values. We have E here, which is our standard exponential, which we have taken to the power of epsilon. And then we have this additive delta here. So what we're trying to achieve here is to make it so that the distributions of our mechanisms are sufficiently similar. Make it so that it's equal, well, roughly equally likely to assume any value, no matter if a certain person is included in the data set or not. So, and we're using our epsilons and deltas to sort of achieve this. Next slide, please. So epsilon and delta here become our privacy parameters. These are parameters that we can choose ourselves to enforce a given level of privacy. So we can decide on our own by how we choose epsilon and delta if we're looking to apply a very high degree of privacy or if we're happier with a lower degree of privacy. So depending on applications. Next slide, please. So if we choose epsilon and delta, for instance, to be very small, what this inequality here will tell us is that the probability distributions of our queries on our data sets that differ by only an element are not going to be very different. They're going to be quite similar, or at least it's going to put a bound on how similar or how dissimilar they can be. And if epsilon and delta are very large, well, then they can differ by quite a bit. So herein lies the strength of differential privacy, that we're able to quantify our degree of privacy. We can put a number on how strong it is, and it's on a continuous spectrum, so we can increase and decrease to suit our needs. Next slide, please. Right. Yes. So now we're talking a bit about some methods on how to apply this. And we're going to start off with the method as it was originally proposed in the original paper. And that is to perturb the answer to a query. So we have a data set and someone queries us. They ask something about our data set. So what we do is that we compute the true answer, so to speak, and then we add a bit of noise to this. And then we give back the noisy answer. So the person receiving the answer knows that, okay, this is roughly correct, but it doesn't know if it's higher or lower than the actual answer. Next slide, please. So the most common way of doing this is to add some sort of noise that is either Gaussian or Laplacian. But basically what this means is that we add noise from a symmetric distribution, right? So it's equally likely to take away as it is to add to our data. And this noise is added in such a way that it's dependent on epsilon and delta, meaning that if we have very small epsilon and delta, so we want to add a lot of privacy, then we're going to add quite a lot of noise. If we want a low level of privacy, then just adding a little bit noise is fine. But obviously there are some drawbacks to this approach, right? Adding noise to the responses to our queries is going to drastically worsen any estimator quality, like statistical estimators on this, with basically the result that you need a lot larger sample sizes in order to get the same accuracy as before. And then we have this, that if we allow people to query against us sort of indefinitely, to just ask the same question over and over, they can just average their answers or the answers that we give them, and that will cancel out the noise that we put on. So this gives us the notion of a privacy budget that we need to sort of limit how many times someone can ask us about this. And finally, this approach, you still need to trust the database holder, right? That we still need traditional security measures to safeguard our data.
So there's a second method that you can also use for differential privacy, which is to perturb the measurement. So rather than perturbing an answer to a query to a database, you make sure that whatever goes into the database is already perturbed when it gets there. There are some different ways of doing this. One of them is commonly applied at the IETF. You remove or encrypt identifiers so that they're garbled when they reach a database. You can also imagine perhaps swapping data between different identifiable flows. So if you imagine in geolocation tracking, you could divide a map into lots of grids, and inside of each box on the grid pattern, you just swap all the individual tracks of traces of individuals, and that would provide some degree of perturbation. You can also randomize responses, which means that with some probability, you allow anyone that inputs data into your database to just provide a false answer to your database. Now, these methods also have drawbacks, the obvious one being that if the data in your database is not true or if it's swapped, you will also worsen estimator quality. So if you wanted to find out some aggregate statistic like what is the average height of people in this room, then if everyone was allowed to say whatever answer for their height, you might not end up with a good answer for that. There's also a need to trust the entity making measurements. So for instance, you need to trust the randomization mechanism used or the swapping mechanism used for your paths. You need to trust that they haven't secretly introduced some other identifier that was not the one that was removed. And so, yeah, it has some of these drawbacks that are really very difficult to work around with differential privacy. Therefore, at the delta differential privacy is not the only privacy needed. It only deals with a very specific case when we are trying to protect the identity of an originating individual for some piece of data when you're making a query to a specific database. So data sanitization and security are still going to remain very important. Data minimization is still going to be probably the primary method that we can use to effectively protect privacy. At the delta differential, privacy is furthermore not the only way that we can quantify how much privacy we are protecting. So there's a very good study from 2015 made by Isabel Wagner and Dave Eckhoff, where they found hundreds of privacy metrics that are all usable to assign a quantification of how much privacy is preserved in a given setting. We can recommend highly going through that survey and looking at the various ways in which privacy can be quantified. Another study, which is here mostly for general interest, is by Duan in 2009, and he demonstrates that as long as you have a sufficiently large data set, which I know many of the people that come to the IETF will work with very big data sets, and they actually contain differential privacy properties in and of themselves at some levels of eta and delta, epsilon and delta. And so Duan is very mathy, so if you're comfortable with statistics, I can highly recommend it too. But just be warned that it invokes the central limit theorem and other methods from statistics that you might have to have prior familiarity with to enjoy. For the IETF community, I think one challenge for differential privacy is that it mostly applies to APIs. Because this is either about how you put data into a database or how you respond to a query to a database, it's going to be application programming interfaces that need to apply these methods. And they are not, at least to my understanding, standardized at the Internet Engineering Task Force to a large extent. But nevertheless, we had some ideas when working on this, which relate to the randomized responses mechanism. So if you have a protocol which is providing some form of information, say about an option, or some other data which is really only used to measure aggregate qualities of the protocol, then you might be able to use randomized responses to introduce additional level of privacy by having a client or a server lie at a predictable or predetermined rate. We've been looking at the weekend on the quick spin bit, whether it's possible to have a predictable false answering to the transition. Also, we've been reflecting on whether explicit congestion notifications could be an application of this randomized response mechanism, because you're really interested in aggregate data, not in the specific data of each entity that provides the response. But we're very open to ideas on other potential use cases that people are familiar with from their own work at the Internet Engineering Task Force. So any questions or comments?
Ben Kaduk. So with this bit on the last slide about potentially introducing random or false data into actual protocol streams, it sort of seems like the key insight that you'll need to do that is to figure out what random distribution to use, because if you just try to use a uniform random distribution for like the bit values, that's going to be most likely not representative of what the normal flow is. And so it seems like this is inherently going to be a case-by-case sort of analysis to figure out, what is the expected distribution and how can we add some structured noise in a way that provides the properties we want.
I mean, so in randomized responses, the typical thing that you would do is some discrete distribution. So you're not in the Gaussian or Laplacian space, but in, for instance, the quick spin bit case, either you spin the bit or you don't. So the natural distribution to choose is Bernoulli distribution or binary two-point distribution. And then you say with some probability P, you give the correct transition. And if it's not P, so the way that I imagine this would actually be implemented in the computer is that you generate the random number between 0 and 1, and then you choose some cutoff point. And if the random number you generated was below the cutoff point, you spin. And if it was above, you don't. And maybe, this is the very simplest case. It's one of the simplest distributions out there.
It's like you're taking a true stream of data and sort of masking it to sometimes not provide the true data.
Right, yeah.
I would just like to mention a quick thing there. Someone mentioned previously the Google Rapport project that they published in 2014. In that one, they do exactly this, right? So randomized bit flipping. So if anyone's interested in that specific application, you can look into that.
Dave Wheeler. I'm quite glad you had this talk. I had some preconceived ideas on differential privacy, and I'm wondering if you can help me clear some of them up. It's from some reading in the tutorials on the foundations of cryptography. They have a chapter on differential privacy, where they claim that anonymization can be easily undone with large enough data sets, and that differential privacy in and of itself protects the individual data set, but can be attacked by using secondary outside data sets that are large enough. So in our world today, right, if I provide differential privacy on my data set, I may be providing information that someone else will incorporate with their own large data set and be able to de-anonymize that information. So I'm wondering if you have some comments on that.
I mean, the observation is entirely correct. Differential privacy is a statistical method. So what you're talking about is sort of similar to this repeated query privacy budget thing that Christopher mentioned, that you're creating statistical uncertainty around one additional individual in the data set. And differential privacy does only exactly that. This is what it can provide repudiative properties for a single individual that is additional to a data set with respect to another query to that data set were the individual not there. But it's not a catch-all for all privacy problems. It only does exactly what it claims to do kind of formally, which is provide some assurances on what the answer to a specific query to a specific database is.
Okay,
yeah.
Thank you.
Wes Hertiker, USC, ISI. So this may be naive. I apologize. My knowledge of differential privacy is spinning up and not leveled off at all yet. But when you are introducing noise to a system in order to deal with differential privacy, and typically access to databases is only done through aggregation functions in order to make it actually work, right? How do you ensure that there's a potential error between the noise itself causes a issue with there's multiple aggregation functions that could end up, sorry, I'm jet lagged, multiple aggregation functions where some may be able to help distinguish the noise between the rest of the material. So if you were able to run 4 or 5 or 6 different aggregation functions, that noise would affect them each differently, and therefore you're actually getting slightly less privacy because of that. Does that make any sense?
That makes sense.
Yeah. Okay, good. It didn't to me.
Yeah, that makes sense. That's a very interesting perspective. I'm not sure if I'm familiar with any sort of work on that. Amelia?
Well, I mean, it looks like, again, a version of the privacy budget problem, that if you make repeated queries to the database, then you can compensate for the noise that's added. The typical way of doing differential privacy is adding noise, but many of you will have studied engineering. You're familiar with stuff like the Kalman filter. There's many different filtering technologies or filtering algorithms that we already use on a day-to-day basis exactly to get rid of noise from measurements. So now if differential privacy adds noise, then reasonably, yes, we can remove the noise by performing the same types of filtering mechanisms that we've been doing to faulty measurements already for 60, 70 years. And it's important to recognize this limitation in differential privacy when you're thinking about applying it to a project, that it does do exactly what it says on the box, and that can be very useful, but it has these limitations, including the ones that you brought.
Okay, thank you. Yeah, I mean, if I had 2 aggregation functions, aggregation function 1 and aggregation function 2, I could run an aggregation function 1 twice, and it would give, I think, the perfect mathematical level of knowledge of how much I'm protecting. But if I run aggregation 1 and then aggregation 2, the cost to me in terms of a budget would be the same, but I may be able to use the difference between those aggregation functions to get a slightly less privacy reduction, for example. So that's sort of my thought, but I don't have an answer.
I'm not familiar with if the privacy budget measures that you can compute from differential privacy now compensates for this level of threat.
I don't know.
Amelia, just a quick concern. So with respect to this spin bit, I think, like you said, the whole thing is about the privacy budget. With enough queries, you can, figure out exactly what you want to figure out. It might be kind of complicated, right, to ask an on-path observer to only take 5 measurements per hour or something.
So you still need some level of trust in the people that make the observations. It's true. When we were thinking about the spin bit also, we realized that one additional complicating factor is that probably there's an IP address or something that identifies each flow. So it's still a very, very nascent idea, at least for myself. But I'm very open to talking to more people about other use cases or about what the results were after our weekend deliberations on the quick spin bit, so we can talk.
I just wanted to remark back on your point about APIs. I think we've been a little bit narrow in this community about what is an API, because it's a human being interacting with a system. But there's no really good reason why an API can't be thought, that something like one end of a protocol connecting with another can't be thought of as exactly that database interaction as well. And similarly, a measurement agent receiving data you could define it as an API too. So I think it's reasonable to imagine that there's this research group can come up with a lot of different approaches where people could use API-like technologies in protocols and measurement.
Yeah, I agree. That's an interesting point of view.
So you've looked at the spin bit so far. Are there any, excuse me, any other specific protocols within IETF that are on your radar and whom you'd like to connect with, people who are developing it?
ECN, explicit congestion notification. Somebody suggested to me could be an interesting application. So if you have any ECN folks in the room, you are very welcome also to talk to me.
And anybody in the room who thinks this might be suitable for them that hasn't been mentioned, please do approach a meeting.
So I think the easiest cases to look at least for now, is places where you have on-off answers. So basically you can use a binary distribution to say, rather than giving a true or false answer, you give a true or false answer with some probability, and all the other things that are more complicated, like if you can choose between 5 different options to communicate in a header, packet header, for instance, then you would need to have a more complicated distribution than a binary distribution. So we could certainly think about that too for randomized responses, but we would have to do a bit more mathematical work to make it still useful for aggregate measurements.
Thanks a lot.
So also the reference list, but you can check it in the slides. Thank you.
Yes, thank you.
Do we have Martin?
Yeah, hi, and thank you also for inviting me. I'm a researcher at the Fraunhofer Institute for Applied and Integrated Security, and I'm also a contributor to the MINUT project. And in my research, I am mostly focusing on decentralized and privacy-preserving identity management. When we started looking into this topic, we first took a look at the consumer identity provider market, which looks roughly like this, with our friends from Google and Facebook claiming around 90% of the consumer identities. Now, per se, this might not be a problem, but if we look into the recent past, some issues arise from this fact. The first one are privacy concerns. So obviously, those companies want to make money and they offer their services for free. And in turn, they monetize this mountain of data they are sitting on. Also, this data can be used for opinion shaping and mass surveillance and data collection, which is an infringement on the user's privacy. Another issue which has become more evident recently is that those service providers, because they are sitting on this huge mountain of data, are now facing increased liability risks, because if they lose this data or if they get hacked for some reason, then they are facing severe risks. And maybe that is also why one of the reasons why competition is not really there for those providers, because actually collecting all this data, maybe the money you can receive from monetizing it is actually lower than the risk you actually face. And obviously the last one is simply the fact that this seems like a market oligopoly, where there can only be one or two or a handful of service providers that is used. This has maybe the reasons of liability risks, but might also just be because they offer so good services in the area of social media that they simply have this amount of users. But identity federation has been around for decades, and it does not seem to take off in any way. So our approach to this problem, or to those issues, was that maybe we need to approach this differently. Our primary objective was that we must enable users to exercise their right to digital self-determination. And in order to do that, we must avoid third-party services that basically allow users to manage their identities and share their data. And this should be done using an open and free service, which is not under the control of a single organization or business. In other words, it should be done through an infrastructure that does not have any other stakes than the user's right to digital self-determination in mind. And third, ideally, which is on part of point 2, is it should be free and open source software. In summary, we want to empower users to reclaim the control over their digital identities. This is also where the name for the idea comes from. So let me explain what Reclaim actually does and how it works. In order to explain what Reclaim does, let's look at some of the tasks that those identity provider services actually provide to users and to websites and services that use them. The first thing they offer is they allow identity provisioning and access control. So the user is able to create an account, basically create an identity, manage his personal data, and share this data with third parties. The service itself then enforces the access control and authorization decisions of the user. The other thing the identity provider does is it verifies and asserts the information of that identity. So for example, if an email provider can say, okay, this is a verified email address of Alice, or a sovereign state might say, yes, this is the user living in Germany, or whatever. It should be noted that the second thing can be addressed, or is addressed recently using privacy credentials based on, for example, non-interactive zero knowledge proofs, which we have seen in the previous talk on Privacy Pass as well. And Reclaim actually focuses on the first issue. So Reclaim ID focuses on the idea, how can we actually allow the user to provision identities, to manage identities and share this identity data, whether it is third-party asserted or not, using a decentralized system. In a nutshell, Reclaim ID combines a decentralized directory service, so a service that is used to basically hold and provision identity data, with a cryptographic access control layer. Now, what does this mean? A directory service, we maybe know Active Directory and LDAP or whatever, but name systems are actually also decentralized directory services. We borrowed here an idea from NameID. NameID uses the Namecoin name system, which is a blockchain-based name system, and allows users to manage identities and data within their namespaces. Now, our implementation of this idea does not use the Namecoin blockchain, and instead uses the GNU name system. And if you're interested in the security properties of the GNU name system, there is actually a talk in this week, I think on Thursday, but I don't remember, by Christian, who will talk on it in another research group. However, the problem with NameID specifically, but in general, when using such a decentralized directory service, is that this data is more or less public. So anybody who has a specific resolver is able to retrieve the identity data and read it. So we added a cryptographic access control layer basically you can always add a cryptographic access control layer using symmetric cryptography and very complex key management. But in order to reduce the complexity of the key management, we're using attribute-based encryption. Attribute-based encryption allows us to define access policies on the ciphertext, which simply reduces the amount of keys we need. So let's look at an example how it works. The user would basically register a namespace in the name system, in the directory service, and populate it with resource records. And those resource records basically hold the user's information, such as an email address. Now, this email address is encrypted using attribute-based encryption, which means the user has a private key and a policy. And this policy says, for example, my email address can only be decrypted using a key that contains the attribute email. And the user does this with every attribute. So in the end, the namespace is populated with a number of ciphertexts which represent the user's identity attributes. If the user now wants to authorize a third party to access a set of attributes in his identity namespace, what he does is he creates a single new key, which is an AB user key. And the user attaches the set of attributes he wants to share to that key. So instead of having to create or share n keys in order to share n attributes, the user only needs a single key. Now this key can be transferred out of bound to the requesting party or to the third party. But in order to facilitate revocation and also key rollover, it makes sense to store a reference of the key in the name system as well, or in the directory service. So in order to now retrieve the data, the third party simply either resolves the user key or he already has it, and then resolves the identity attributes from the directory and decrypts it. Attributes which are not attached to the key cannot be decrypted by the requesting party. Now, obviously, if we wanted to use such a system, we do not want to burden the user or the third party, for that matter, with any kind of key management and name system specifics. So what we did in our implementation and in our design was that we built an OpenID Connect layer on top of this idea. So under the hood, it basically works like I just explained in this example, but from the point of view of the user and the integrating website, for example, it works just like any generic OpenID Connect provider. So it basically also adheres to the OAuth protocol. Although I should say that the OpenID Connect protocol and the OAuth protocol are not specific enough to actually address, for example, if the requesting party or the website wants to have a specific credential asserted by a special identity provider. This is currently not possible due to the protocol being still very simplistic. But in general, this works and adheres to the standard. So in summary, we have implemented this idea as part of GNUnet, which is a peer-to-peer system. There's a functional proof of concept demo also on GitLab, which you can find under the link here. Although it is not really finished, it's still very rough around the edges, and we want to make it a bit more user accessible because, yeah, it's still coming directly out of research, and we're still working on making it practically usable. Yeah, thank you. Any questions?
Thank you. Alex Meyerhofer from Nikto.at. I was wondering, at the moment that you associate the public key of the attribute-based encryption with a name on the new name service, new name system, aren't you like reducing privacy significantly, because then it allows somebody else to like collate various ABEs via the same name? So if I put like different proofs or no idea how you call them under a single name, then it's very easy for somebody else to like discover that this was produced by the same identity.
Yeah, so basically there's no distinguish, so you always know which identity it is because you're looking up a specific identity namespace. Or okay. Are you talking about if you're using the same attribute in for different identities? Because, okay, if you're using different identities, then you're probably using different ABE private keys internally, which makes it indistinguishable from each other. However, you could argue that using, for example, privacy-preserving credentials, so zero-knowledge proofs, as attributes, does not make that much sense because you're always identifiable as this single identity. So yeah, that's.
Yeah, well, I'm trying to compare that with other self-sovereign identity systems like Sovereign or Uport, where you have a pairwise relation, and you essentially cannot discover a real identity unless that person wants to reveal it. Essentially, so but by putting it behind a single name, that's often a criticism with the DNS, like, oh, you put it in the DNS, so everything is like under the same name, so you know exactly who that is.
What you can do, obviously, if you use DNS as an underlying name system, you have that problem.
But you also have the name service, the problem if you use GNS.
Yes, but in GNS or also in Namecoin for that matter, you can just create new pseudonyms whenever you want. Okay. So obviously, if you use the same pseudonym, you are trackable, but you can just create new ones at will because they're effectively just public-private key pairs.
Okay, thank you.
Hi, Vittorio Bertola from Open Exchange. I have a question, which is also, I'd say, a comment for everyone who's interested in these kind of things. Having worked for some years now on a project which is very similar, except that we use the DNS because we don't have a problem with the DNS. And so, I mean, the real problem now is that there are like 100 different projects that are trying to do these kind of things. Well, in the real world, there are only basically two, I'd say, single sign-on identity systems that are in wide use, Google's and Facebook's. And maybe in Europe we have the EIDAS public identity system for taxis and this kind of stuff. So I guess that the problem that we have is that I think also people agree that we need something like this which can put the user back in charge, but how can we get adoption? And the real problem is actually that we are dividing in like I'd say 50 different projects with slightly different ways of doing the same things, and some people use the blockchain, some others use it, but in the end with the same objective. But since we are so divided, we don't get anywhere. So I don't know if you have any reflection on this or strategy for adoption or whatever.
Yeah, I agree wholeheartedly. So yes, but I think if all of those projects actually, for example, use the standard OpenID Connect, for example, to use them, then if the users become, if you offer the software to users and show the benefits in terms of privacy, for example, they might just start using them. So there's no reason why you cannot put a generic OpenID Connect discovery button on a website. So.
I'm Watson Ladd. I'm from Cloudflare. My question is about sort of the economics of getting websites to integrate. Like one of the reasons I think websites have Google and Facebook as login options is that users already have these and you just click through. So for users, there's a benefit to SSO. How do you get websites to integrate another SSO given that there's limited space and users don't like options? And how do you get users to see the benefits of adopting an SSO thing if you don't have websites that integrate it?
Yeah, that's the chicken egg situation. I don't have a solution for this. I would probably address it first in getting the users to want it, and then websites will just follow. I think that's the path you usually have to take. But I don't have a solution for this per se.
And my other questions about how do you? So one of the reasons that I, for instance, use Google Single Sign-On is, for DigitalOcean, for instance, it is the most secure way to log on to DigitalOcean because you can use a two-factor authentication device. They don't have one any other way. How do you address that level, the authorization issues?
Okay, so the DigitalOcean, for example, probably. So you want to log in using two-factor authentication, but I'm assuming DigitalOcean doesn't really care how you log in. Basically, that's something that Google just does for you. So that then depends on the actual concrete implementation, because OpenID Connect doesn't really do authentication, so it's not an authentication scheme. Obviously, you could extend it, but that's not really in scope of the system.
Well, I'm not sure exactly what they're using, but you have to be signed into your Google account before you can click the button to sign in.
Yeah, but they don't care how Google does authentication, I'm pretty sure. So,
but they're piggyback on it. They don't have to do the work. Google does it, and it's up to you how to do it.
Implicitly, they do it, right?
So, Leif Johansson, I think the whole notion of sort of pinning this on the back of SSO is probably a mistake. Progress in the WebAuth space is probably going to make SSO as a value proposition pretty useless anyway. I don't know what that means for Google and Facebook sign-ins, probably nothing. But in the cases where federation actually works, and there are a number of cases where it does work, is because relying parties actually want and get information about users, and users want to share that information with relying parties in controlled ways. Like Eduroam, for instance, where you're basically sharing an affiliation, right? I'm part of a club, and that gives me access to the network. In those situations, it has nothing to do with SSO, and it has nothing to do with, at least not perceived user privacy, but it has everything to do with UX. So I think to make progress in this space, you actually have to focus on UX, not technology, because that's where the really hard problems are.
Yeah, I think maybe to just comment on that briefly. What it does is actually it's just a service. Any OpenID Connect provider just allows or just provides a service that allows the relying party or the website to retrieve this identity data when the user is offline as well. So it's not just a direct interaction and a single sign-on issue. It's also a service that provides this identity data as a service.
Right, and that's a perfect illustration of this, right? Because like all of the projects that somebody mentioned, there are 100 of these, right? And they all focus on the back-end part of this, right? They all focus on the technology of the blockchains and the zero-knowledge proofs, et cetera, right? But and then they all add a connect or a SAML front end because it all has to live on the web. Because nobody has figured out how to build usable UX for the user, right? And whether it looks like, and some people think it looks like a wallet or something, right? And just replacing a very large identity provider with a very large wallet provider. Because, but nobody can figure out how to get users to want to deploy the client. Right? I suspect that all of these projects should just stop worrying about like blockchains and shit like that, and start thinking about how to get users to want to use use a new UX. I think that might help.
Yeah, I agree.
Hello, Tobias from LMU. I didn't really get what you store in the DNS system. Do you store the key to decrypt the email address? So in your example.
Yes, we both install the encrypted email address as a record. And we also store, when we also authorize a relying party, then we have to issue a key that is used to decrypt. And we also store that in the name system, encrypted, for every relying party. Because if at some point we need to do revocation, we might need to update some of the decryption keys. And then we basically store them in the name system. So in the next time when the relying party needs to access the attributes, it can retrieve them from the updated keys from the name system.
Okay, and how do you do the authorization for the key?
Basically, when we're doing the OpenID Connect flow, the client ID serves as the public key of the client, and we encrypt the keys with the public key of the client, so that only the client can then retrieve and decrypt the ABE key.
Okay, thanks.
Thanks, Martin. Brooke, looks like we have time.
Yeah. Hi, I'm Brooke Schofield. I work for Géant. This is my first IETF, IETF sort of a meeting. So anyway, I'm here to talk about the next generation of the internet. So if you have been to a welcome, and presumably the first time you turn up to IETF, there was a welcome, you would have at some point come across the mission of the IETF. And this is to make the internet work better. Now, NLNet Foundation have a goal to create the internet of tomorrow. And as such, they got approached by the European Commission to work on a series of documents because, well, they discovered this to be a problem. This is from a presentation by Michael Lennart, who's not here at the moment, that actually the internet is not necessarily serving what we hoped it would serve. And so in a short space of time, it's, well, as you can see from the presentation today and the problems you're trying to solve by being in this room, it doesn't always do what we want it to do. And so to create a next generation internet, a user-centric internet, how are we going to rebuild a currently working system, working to some definition of working? Because there's a lot of moving parts, and you know, trying to build something new or improve the user privacy on top of that working infrastructure is going to be a challenge. So NLNet Foundation did a big analysis, some consultations, produced some paperwork and a vision, and that has resulted in a European Commission funding stream to be able to explore this area. In fact, it was a very big sort of architectural document of all of the things you could possibly look at, and then they decided that trying to work on all of those things individually isn't going to work. The heap would crumble. So we have this next generation internet open call process where a few of these open calls are kicking off right now. It's being built with a larger ecosystem. So NLNet Foundation happened to talk to GÉANT, the organization I work for. We're the Association of Research Networks in Europe. The RIPE NCC, lots of ISP groups, in order to get their feedback on what work we need to undertake in order to improve the situation. And so there'll be a lot of funding programs coming on stream in the coming years. And at the moment, there are 4. Actually, it'll be on a later slide. So there's this NGI vision document. You can go to ngi.eu/vision and get a copy of this report that NLNet Foundation developed. And this shows the current funding stream that's coming on board. So this is a pitch for you to come with your ideas to these open call processes and seek funding to complete this work. So at the moment, there are 4 active open calls, 2 in green run by NLNet Foundation, a distributed data, distributed ledger group in orange, and this privacy and trust enhancing technologies, which is the project that I'm involved in the consortia. There's also 3, I think the deadline for these are the proposals for people to run these open call systems. So there's 3 projects that are currently, the deadline is real soon now. It may be at the end of this month even. So those will turn into, they're seeking a coordinator to run a funding call so that you can target these additional areas. And there's more areas that are coming on stream within this NGI sphere. So NLNet Foundation are looking after search and discovery and privacy enhancing technology. These are open calls that have a very low barrier to entry. Not everyone's always successful, right? But they offer money in the range of 5,000 euros to 50,000 euros. They have and they run these calls regularly. Every 2 months, these calls pop up throughout the cycle of this project. NLNet Foundation also offer other funding opportunities. So check their website for more. GÉANT is part of a consortia on privacy enhancing technologies, and we have money up to 100,000 euros for, unfortunately, a slightly weightier application process. And the Ledger project offers up to 200,000 euros on distributed data, distributed ledger technology and blockchain projects. And you can find this information on the ngi.eu website. So yeah, these are the currently open calls. The deadlines are ever so slightly different. So NLNet Foundations run every 2 months. Their deadline is the 1st of April, but also on the 1st of April, a new call will open for them and run for a period of 2 months. NGI Trust and Ledger have open calls that end on the 30th of April. And we'll be running additional calls later in the year. So we're not as agile as NLNet Foundation to have this very rapid process, but we hope these proposals will be slightly longer, more involved, and we provide some other support infrastructure in getting your applications across the line. You can also contact us and we can give you advice and guidance in the lead up to submitting a call, but once you submit something, we can't talk to you until the assessment is out. So feel free to talk to us leading up to that. And this is how you can directly contact me or visit the NGI website and look at open calls. Ask questions, talk to me in the break. I'm here all week. Tip your waitresses.
This is a European initiative, right?
It
Is there
is.
any restrictions on who can apply, what countries they're from? Obviously, the fact that I happen to be from the UK is just pure coincidence.
You can still apply. It has to be for the benefit of Europe. So it's not exclusively for projects or people resident in the European Union. It does make it easier. And once the individual open call projects have done their assessment, there's actually a final group within the European Commission that decides whether it passes this bar of being beneficial for Europe or operating within Europe. So there are things outside of Europe that are beneficial to Europe, but it would make more sense if you had a project partner that was in Europe, and you definitely focused your proposal on how it is beneficial for Europe, just not beneficial for your project's work.
Okay, thank you.
Great. So that concludes our meeting. Are the blue sheets still floating around? Thank you.